many thanks for the introduction, and also for giving me the opportunity to speak here, and also, yeah, sorry for the confusion. I hope now everything will be finally okay. So the talk is about approximating high-dimensional functions. More precisely, in many computational problems, one is interested in approximatively computing or approximatively evaluating high-dimensional functions, say functions from the d-dimensional unit cube into the real numbers, or more generally from some a, b here, two real numbers, a, b, and into the reals. And yeah, and then one wants to approximately compute evaluations of such functions. Okay, specifically, you can think of computational problems from financial engineering, where one wants to approximatively compute risks and or approximately evaluate financial products. And here in such applications, the dimension corresponds to the number. I mean, two parties have two contracts, or several parties have contracts with each other, financial contracts, and the dimension corresponds here to the number of financial assets, to the number of underlines in the involved hedging portfolio, say the number of stocks or commodities or interest rate in the involved hedging portfolio. And another situation where such high-dimensional approximation problems appear is in operations research, where companies intend to optimize their decisions, intend to optimize their behavior to maximize their profits or minimize their costs. Say in the situation of optimal control, stochastic optimal control problems. Another situation where such high-dimensional approximation problems appears in environmental sciences, where one tries to model biodiversity in an ecosystem where each dimension corresponds to different properties, different traits of the considered species, of the considered individual in the model. And say you can think of birds in the South American continent, and then, for example, the temperature on which one species or would like to live, or the average temperature, and also the standard deviation of the temperature. These are all different kinds of traits, and building, so usually like something like 8 or 10 dimensional models. Another situation where such high-dimensional approximation problems appear is in nonlinear filtering problems, where only partial information of a given physical system is given, and then given that information, one wants to know the best approximation of the density of the current state of the system. And in many such computational problems, one wants to approximatively evaluate or approximatively compute high-dimensional functions, such as, for example, here, a function u from the d-dimensional unit cube to the reals, where d is a large number, and large here means something bigger than 3 if you want, and starts like with something 4, 5, and goes to 10 or 100 or also thousands of space dimensions. And approximation methods for partial differential equation or for such problems in the literature, such as finite difference approximations or finite element approximations or sparse grids, they suffer under the so-called curse of dimensionality, in the sense that the number of computational operations and the amount of memory used to calculate with such computational methods grows exponentially in the problem dimension. For example, you can think of, think of the situation where d is equal to 2. So we want to approximatively compute or evaluate a function from the 2-dimensional unit cube to the reals. Then we introduce here coordinate axis x and y, and then we use introduce a natural number n, which can be, for example, like 10 or something like this. And then we have here this is a 1, here 1, and here 0, 0. So we divide now the x-axis into small subintervals, each of length 1 over n. And similarly, we also divide the y-axis into small subintervals of size 1 over n. And then for each of these subintervals, we get an associated grid point here. So here it would be these grid points and these grid points and so on, and here also on this axis. And now for all combinations also all these grid points. And then overall, one has something like, one has here n to the power of 2 many grid points, and this results in an error of about 1 over n for the precision, up to a constant, of course. Okay, and now in high dimensions, this is something like the number of grid points would be n to the power of d. And now when you relate, so here this means that so epsilon or n is equal to epsilon to the power of -1, and then plugging this in results in a computational effort or number of grid points in terms of the precision, and the dimension is epsilon to the power of -d. So you see here the dimension here grows exponentially in the exponent of the problem. And with such methods, so if you think, for example, you can think of a precision of 1 over 100, then you have here 100 to the power d grid points, and with such methods, it's impossible to compute reasonable approximation, even if all the fastest computers in the world are used together. So if you are in, like, say, yes. Sorry?
Just one quick question. Why did you put sparse grids in this context also? Because it's an argument that you're making usually doesn't go with that, right?
I mean, sparse grids, they also grow. They significantly reduce the computational growth in the dimension, but still the computational effort also grows exponentially in the dimension. Okay, something like, you know it better than me probably, something like e to the power of log, but there's still some d in the exponent. So that's why they still suffer.
Okay, so just to comment on that, it depends on the functional space that you're working. Actually, in particular functional space related to some kind of PDEs, even in infinite dimension, this will not be the case, right? They will have under the curse of dimensionality. But again, the statement is very much related to the regularity space and the anisotropy that is behind the functional space you use for the approximation. Okay. That's the only thing I wanted to say. If you change the space, they may be subject to the curse of dimensionality. In another space, they may not. So the question is not, I mean, it doesn't have a general answer, right? I mean, you have to go to a particular statement.
Yeah, I just said to say that I have, when I looked at the literature, I've not seen a paper where with sparse grids. I see one paper where the time horizon is very small, and then there was a 20-dimensional PDE source, but I've never seen with sparse grids. I've never, and with for these other methods, maybe something like
I
5 or 7.
I can give you references, but I mean, it's not just us. I mean, Schwab and collaborators. But again, it is extremely important to work with, what is called weighted spaces that have like weights in the derivatives, and then of course one can get something, but it's not general. What I'm saying is that the answer may be yes or no regarding the curse of dimensionality, depending on which is the PDE and which is the functional regularity that you have. But that's it. I mean, that's why I wanted to kind of separate it from brute force tensor type of methods, right? Because the answer is probably independent.
Yeah, this 20-dimensional paper I had in mind was precisely by Christoph Schwab and co-authors. Anyway, but I'm look forward to your references. Okay, so
okay.
Now, but one method which overcomes this curse of dimensionality is this Monte Carlo method, based on the Feynman-Katz formula, where somehow which works very well in the case of high-dimensional linear Kolmogorov PDEs. Okay, so in such situation, one can reformulate the deterministic PDE UTX as an expectation of a functional of a stochastic process. And then instead of introducing some grid in the space variable, one uses a Monte Carlo average yeah, for approximating this expectation, and then one can probably show that this method grows only polynomial in the problem dimension and in the inverse of the precision, and thereby overcomes this curse of dimensionality. So yeah, so usually, or depends, this error is something like e to the power of p multiplied by epsilon minus 2 plus delta, where delta is a small number. That's usually a complexity one can establish in this situation here, where this constant is depending on p, and also, yeah, sometimes also on delta. Okay, so, but this method, this works very efficient, and one can easily solve like maybe 10,000 dimensional PDEs with this method, but it only works for linear Kolmogorov PDEs where the one is interested in the evaluation of the PDE at just one specific point. Another, yeah, so then in 2017, together with Jikin Han and Wenan, we proposed some scheme which we refer to as deep BSDE method, where somehow the idea was to approximate the solution, a solution of high-dimensional PDEs by means of the solution, or respectively the derivative of solution, by means of deep neural networks. So first, the solution of the PDE is reformulated as a stochastic optimization problem, as a stochastic learning problem, and then the solution, or respectively the derivative of the solution, are approximated by deep neural networks, and then the resulting finite dimensional optimization problem is solved with stochastic gradient descent type optimization methods. And so another way you can say it's in this work we use we solve high-dimensional PDEs approximatively by means of techniques with deep learning. And the numerical, there was no proof in this paper. There's just some derivation and some numerical simulations, but these numerical simulations were quite encouraging. And this is also not the only work. There are a lot of other works where particularly I want to highlight here this work of Sirignano and Spoupopoulos with this so-called, what they call deep Galerkin method. Okay, so, and there are still much more works also with much more sophisticated approximation methods. Okay, so let me just give you a very brief introduction of what you can think of as artificial neural networks, as an artificial neural network. So roughly speaking, you can think of an artificial neural networks as or the realization function of an artificial neural network as the composition of functions, so of a finite composition of functions. So first you use an affine linear function, and then a certain fixed nonlinear function, then an affine linear function, and then again a fixed nonlinear function, and then again an affine linear function. And when you so usually one draws such functions in a picture. So you see here, this corresponds to this figure here illustrates an artificial neural network, or the realization function of an artificial neural network here from a 5-dimension, from the R5 here. There are 5 neurons here on this input layer, and each of these neurons corresponds to 1 dimension of the argument space, and into the R3. So each of these nodes here corresponds to 1 dimension in the codomain of the function. And then, so this function consists of multiple compositions. So first we have here one affine linear function, then here a nonlinear function, and the fixed nonlinear function. And this then results in a vector in the R6. So this is this first affine linear function combination with a nonlinear function mapped from the R5 to the R6, and then from the R6 to the R7, again one affine linear function, and then the fixed nonlinear function, and then from the R7 to the R3. Okay, so again an affine linear function, but here usually often there's no nonlinearity anymore, nonlinear function. And maybe the most popular choice for the nonlinearity, which is applied here and here, is the multidimensional version of this rectifier function. So that we take a real number x and map it to maximum of x and 0. Okay, and then the multidimensional version
Sorry, Arno, sorry for interrupting, Arnulf. Maybe just me, but I don't hear you anymore.
I don't hear him either. I think he froze actually.
Yeah.
Yeah, the video is frozen.
I think the connection is.
And he doesn't seem to hear us because we see your tablet moving. I just did at least.
Yeah, maybe what he could do is to cut the video feed to improve the, the bandwidth. Tell him to do that, Sebastian, to cut his video.
Arnulf, I mean, could you maybe turn off your video to maybe save some bandwidth, and then maybe we can at least hear you again. Let me also, okay, the video is off. Can you say something? So it doesn't, let me check. Can you hear us? Okay, Arnulf can hear us. That's good, of course, but we can't hear you, unfortunately.
Okay, so a neural network, you can think of it as a function, or in this example, it's a function here from the R5 to the R3, the realization function. And it's here one affine linear function, and then comes the nonlinear function, and then this result is a vector in the R6, because we have here 1, 2, 3, 4, 5, 6 neurons, then again an affine linear function, and a nonlinear function, the fixed nonlinear function to the R7, 1, 2, 3, 4, 5, 6, 7, and then an affine linear function here from the R7 to the R3. Usually there's no nonlinear function anymore here, so just an affine linear transformation. And this nonlinear function may be the most popular choice for the nonlinear function which is used here and here, is maybe like the multidimensional version of this one-dimensional rectifier function. Okay, so this rectifier function takes an x from the real number and maps it to maximum x and 0, and again a real number. And so this is then applied to each component of this 6-dimensional vector, and here of this 7-dimensional vector. That's called the rectifier function. There are also other frequently employed activation functions, but maybe this multidimensional rectifier is maybe one of, or maybe the most popular choice in numerical simulations. Okay, so this you can think, roughly speaking, of an artificial neural network. And now I want to show you one numerical simulation of such deep learning schemes for high-dimensional PDEs. Okay, so this is here for an Hamilton-Jacobi-Bellman PDE, which somehow links stochastic optimal control problems to nonlinear or semilinear PDEs. Okay, or nonlinear PDEs. So this basically is the solution of this PDE is basically the cost to go function in the specific optimal control problem to control a Brownian motion in the d-dimensional space. And here in such optimal control or portfolio optimization problem, one often uses here a concave initial condition or terminal condition for the PDE. And then here you see some numerical simulation result for such a deep learning based approximation scheme for PDEs. You see here, for example, in 10 space dimension, one gets a relative approximation error of 1/100, and then in like 1 minute of CPU time on one computer with a GPU. Okay, and then you see here in maybe say 5,000 dimensions, one still gets an error of 0.2% relative approximation error, and 400 seconds of computation time, and even in 10,000 dimensions, the relative approximation error is 0.1%, and here in about half an hour. Okay, so this is just one example. So these are all approximations for the solution of the PDE at time 1 at 0.0. And you see this are some hyperparameters for the approximation scheme. And this, you can find this simulation in the below mentioned reference. This is not the scheme from this work with Chicken Han and Wayne and I mentioned, but another variant. As I said, there are also plenty of other approximation schemes and numerical simulations for challenging high-dimensional PDEs available in the literature, and most of them, or many of them, look quite encouraging when it comes to the question of whether the curse of dimensionality might be possible to overcome the curse of dimensionality with such methods. And until today, there is no proof, okay, that such methods do indeed overcome the curse of dimensionality. There's even not a proof that such methods do converge, even in one dimension. Not even if you ignore a rate of conversion, there's also no proof that such methods do converge actually. But the numerical simulations are quite encouraging. And now there's one result which shows somehow that deep neural network have the capacity to overcome the curse of dimensionality when approximating semilinear PDEs of a similar form of this. And this is the result which I want to show you now. Okay, so in detail. So here it's a semilinear PDE. So big T is a time horizon. Yeah.
Arnulf, can I ask you before you jump into this result? I heard people making kind of statements of the following type, that in some problems, actually when you start raising the dimension, the discretization somehow becomes simpler because there is some kind of strange law of large numbers that people yet do not understand, that makes essentially the solution to behave in a very simple way with respect to the dimensions that you have in your problem. And therefore, not only neural networks can approximate nicely this kind of high dimensional problems, but other methods as well. Have you heard anything of that kind? I mean, here you suspect that there's something at play in this problem as well?
Okay, when you ask me, do I suspect? So, I think there are certainly examples where it seems that the problem gets maybe easier in high dimensions. So, for example, you can here also
just to give you,
see that the error, on this example,
yes.
okay, yes, that the error somehow. But you also have to take into account we also train a bit longer in higher dimensions, but still, okay. But I think. But I think this is just, I picked this example because it's a very good PDE because it links optimal control. And so it's, I think, very interesting.
I know, but I think the question that I have is related to the symmetry. Because,
but I think there are other PDEs where you cannot at all observe such a situation in the numerical simulation, where it always gets more difficult and more difficult in high dimensions. Okay, so this is the first comment I want to make in this. And also the other thing is, for this multi-level, for this nonlinear Monte Carlo scheme, this multi-level Picard there, one can also provably see that the curse of dimensionality can be overcome. And I don't know, besides this multi-level Picard simulation, which are quite restricted to like certain class of nonlinearities, which quite restricted class of semilinear PDEs, and this deep learning approximation scheme, I don't know any situation of a PDE which has some practical relevance, okay, and which can be approximated, say, in high dimensions. Okay, so I don't know. I have not seen any numerical simulation result of a situation where somehow a practical relevant, okay, it's of course a bit, a practical relevant example has been approximated in high dimension with schemes beside these deep learning schemes, or this multi-level Picard method. I haven't seen any convincing numerical simulation. So I don't know whether, I think you're completely right, or it's probably clear that there are certain examples. This function, why also I choose this example, because it can be transformed to a linear PDE, and by means of the Cole-Hopf transform, and then then you can use plain vanilla Monte Carlo together with this transformation to get the reference solution. Okay, so that's why I also choose this example, because somehow it has a reference solution. But then for other examples where we don't have reference solution, we compare like the multi-level Picard against the deep learning approximation scheme. And so what example, for example, you can think of have in mind, I mean, when you think of like something like sine of u, okay, so something like this, u dot equal to sine of u. And then I don't know any approximation scheme also, yeah, which can approximate such PDEs. I don't know simulation where in 100 dimensions, say, yeah, besides such deep learning approximation scheme and the multi-level Picard method with this simple nonlinearity here. Yeah, but so I would say if I hear again your question, so if I then I would say there are certainly examples where this happens, okay, but then that there are also other schemes. I mean, probably there are also other schemes, okay, but I mean that there are other existing schemes which somehow are published and where studied in the literature. There I would be a bit more pessimistic actually, okay. But that there are other variant of schemes, I would say that's most likely to be the case, that there are also other types of schemes. Okay. Okay, so now let me go to this theorem. So okay, so let t be a real number bigger than 0, and p. So that's we are here on a semilinear PDE from the time interval from 0 to t, and then we want to measure the error in the LP sense, okay? And then we have a real number kappa, so that's the role of this parameter p, and then kappa, this real number, is to describe some regularity assumption on the solution of the PDE. And now we have a Lipschitz continuous nonlinearity. So this function f here, and then we also, when we want to make a statement about the curse of dimensionality, we want to make a statement about how the complexity, how the number of parameters of the network grows in the problem dimension. Then we cannot just fix a 20-dimensional PDE and make a statement about this PDE, but we need to consider a whole family, a whole sequence of PDEs. And this GD here denote the initial conditions of the PDEs, because we now have a whole family of PDEs indexed over the dimension, and these GD here are these initial conditions. And then UD are at most polynomial growing solution of these PDEs here. So these are the solutions now with this semilinear heat PDE with this Lipschitz nonlinearity. Okay, and here in this statement, I mean, this is here the Laplace operator, which has a lot of smoothing, but that's not the essence of the theorem. Okay, so this operator could be replaced by a second order operator, which is somehow very degenerate, or also just a first order operator. Okay, but then the problem is maybe too easy, but okay, could be just replaced by a second order operator, which is very degenerate. So that's not essential here, but that one has this smoothing effect of the PDE. And then, okay, these are the initial conditions of the PDE. Okay, so u at time 0, UD is equal to GD. And now, okay, if we want to approximate, so the idea of this theorem is somehow we assume that the initial condition can be approximated without the curse of dimensionality by deep neural networks, and then, or by neural networks, and then as a conclusion, we can approximate the solution of the PDE also without the curse of dimensionality. And so to be in the position that we can approximate the solution of the PDE without the curse of dimensionality, somehow we need some regularity conditions, and somehow one quite natural assumption is that the solution itself doesn't grow, and also its derivative doesn't grow like exponentially in the problem dimension. Okay, so this is here formulated by this assumption that for all x in the RD and all for all d and all x in the RD, we have here that the GD of x and also the gradient, which is somehow not, yeah, can also be relaxed, this condition here with the gradient, but that the solution, the initial condition at least, needs to grow at most polynomially in both the problem dimension and the space variable. And now we precisely formulate these neural networks. Okay, so here this multidimensional rectifier function, which is here just these functions ML from the RL to the RL. so which is ML of x1, x2 in XL is just equal to maximum of x1 and 0 and maximum of x2 and 0 and so on, maximum of XL and 0. And now after having formulated this nonlinear function, we want to formulate the affine linear transformations in between this nonlinear function. And they are here given by this set boldface n. Okay, so they are described by this set boldface n. So each affine linear transformation is described through a matrix vector pair. Okay, so this here is a set of all Ln times Ln minus 1 dimensional matrices. And this here is a set of all Ln dimensional vectors, are real Ln dimensional vectors. And this Cartesian product is then all matrix vector pairs. So one matrix and one vector. And this is a set here of all matrix vector pairs. And then one considers here the Cartesian product from N1 to L. So this is a set of all L tuples of matrix vector pairs. And here we allow now, so these Ln correspond to the dimension. When you think of the figure I had on these hidden layers, okay, from between these affine linear transformation, and we want to allow any of these dimensions. So we make here a union over all L0, L1, LL natural numbers, and L we also want to allow any arbitrary lengths. So in the previous figure and also in the numeric simulation, there was L equal to 3. We had 3 affine linear transformation and 2 of these hidden layers between and 4 layers overall. And that was in this figure and also in the numerical simulation on the previous slide. And here it can be an arbitrary natural number, which is also crucially needed in the proof or the statement of the proof. And now to each of these functions, to each of such L tuples of matrix vector pair, we assign a function. So we could define here the function R, which takes elements from N and maps it to a continuous function from the Ra to the Rb, where A and B here are any arbitrary natural numbers, in the sense that for all L and all L0, L1, and so all LL natural numbers and all phi, which is now here an L tuple of a matrix vector pair, and all x0, x1, x0 and RL0, and xl and RLL, with a recursion that xn is given as now here this multidimensional version of the rectifier function applied to wn xn minus 1 plus bn. Okay, so this here is the affine linear transformation, and then here this nonlinear activation function, this multidimensional rectifier function, that is the recursion for xn. So first we have x0 is arbitrary, and then x1 is given to this recursion, then x2 and so on. And finally, the realization of the realization function, so r phi of x0, so here phi is this neural network, this L tuple of such matrix vector pair, is assigned for any x0, it is assigned WL applied to XL minus 1 plus BL. So at the output, we don't apply this nonlinear activation function anymore, but just the affine linear transformation. Okay, and now we want to also measure how much memory we need to store such an object, such a function, such an L tuple here phi on a computer, or more precisely, we want to measure how many real numbers, scalar real numbers, do we use to store such an object. And this is the role of this parameter function here, which is a function from the set boldface n to the natural numbers. So which is just defined, so it counts the number of parameters. So for example, or the precise definition is P of phi is equal to the sum from K1 to L, and then LK multiplied with LK minus 1 plus 1. Okay, so but this is of course nothing else but the sum from K1 to L, and then we have here LK multiplied with LK minus 1. These are the number of parameters for the matrix, plus LK for the affine linear transformation, for the inhomogeneity, for this number of real numbers in the vector, and that then defines this number of parameters. So these are just the number of scalar real numbers used to describe such a neural network. For example, I give you one short example. Okay, so if phi is equal to, say, now we have here 1 minus 1 and then 0 0. Okay, and then we have another matrix vector pair 1 minus 1 and then here 0. So in this example, that's an element now in this set of neural networks. I mean, we have here that we have, it's a 2 tuple. Okay, so it's a pairing. So this here is the first affine linear transformation, and this is the second, describes the first affine linear, this is the second. So in this example, we have L0 equal to 1. Because this is a 2 times 1 matrix, so we take here a one-dimensional input, and then we have L1 equal to 2, because this is a 1 times 2 matrix. So now, after this affine transformation, we are in the R2, and then we apply this affine linear transformation. So after this affine linear transformation, L2 is just 1, because here we take a vector in the R2 and multiply it with this matrix, so we get a real number. So and this would be so L would be equal to 2, okay, big L, and L0 would be 1, L2 1 2, and L2 1, and the number of parameters here in this example would be just equal to 7. Okay, so we have here 1 2 3 4 5 6 7 real numbers, and the realization function of this in this example, so R phi of x0, which is now a real number, would be equal to x0. Okay, one can easily calculate this, that this represents is the identity function by means of such neural networks. Okay, and now we need one more assumption for stating for the theorem, and that is that the initial condition, they can be approximated by neural networks without the curse of dimensionality. Okay, and that is here formulated by this assumption. So GD epsilon, so there exists a family of neural networks indexed here over the dimension and the precision epsilon. Yeah, such that the number, so for all dimension D and for all epsilon, we have that the number of parameters of these networks is smaller or equal than this constant kappa multiplied by D to the power of kappa multiplied by epsilon to the power of minus kappa. So it's a polynomial in dimension and the inverse of the precision. And also we have that the error, the distance, okay, between the initial condition at point X and the realization of these networks at point X is smaller or equal than epsilon multiplied by kappa multiplied by D to the power of kappa multiplied by 1 plus norm of X to the power of kappa. So you see the right-hand side here converges to 0 as X converges to 0. So in particular, we get that these realization of these networks converge pointwise to the initial conditions. Okay, and they not only pointwise, but even locally or uniformly. Okay, so and with the cost, I mean, with the number of parameters growing only polynomially in the dimension and the inverse of the precision. Okay, and for example, you can think of GD of X if you, for example, have equal to the maximum of all components, they satisfy this assumption. Or also if you take here any smooth function, say sine of maximum and then cosine of X, also comma dot 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 cosine of XD, for all such concrete examples, one can verify that this assumption is indeed satisfied. Or also this example we had there on the previous numerical simulation, square root of the standard norm, that's also satisfied, or any power here of the standard norm, or also a smooth function out of this also. Okay, so these are all examples of initial condition for which one can all verify, not very challenging, that they satisfy this assumption. And then the statement is of the result that then under this assumption there exists a family of neural networks indexed over the problem dimension and the precision, and as well as a constant, a real number C bigger than 0, such that for any dimension D and for any precision epsilon between 0 and 1, we have that the error, the LP distance here between the exact solution and the realization of the neural network is smaller or equal than epsilon in the LP sense, and also the number of parameters of the neural network is bounded by a constant multiplied by D to the power of a constant multiplied by epsilon to the power of minus C. Okay, so grows only, the number of parameters grows only at most polynomially in the dimension of the problem and the inverse of the precision. And let me also add a few more comments. So, okay, so here in this result, it's really essential that here the dimension, the neural networks, that they are deep neural networks. I mean, that this L is large, even if for the initial condition, one can use shallow neural networks with just 2 affine linear transformation. It's essential that here these neural networks are deep. And also, I mean, but somehow one needs to also take into account, I mean, all these neural networks describe low dimensional, I mean, the realization function describes somehow some, if you want, generalized low dimensional submanifolds or lower dimensional submanifold of all continuous functions. So in some way, one cannot say that deep neural networks can represent more functions than shallow neural networks. But somehow, what is here in the proof intensively used, somehow deep neural networks seem to fit more well to the structure of those semilinear PDEs, say, of these kind of problems. So that's why for deep neural networks, such a theorem can be established, and for shallow neural networks, I mean, yeah, there are also certain counterexamples that is impossible to establish, not exactly this kind of result, but results of similar type. Okay, and yeah. With this last comment, I would like already to close the talk, and thank you very much for your attention.